All right, let's get started. Welcome to, this is CS4510, L13A, and the topic is the art of reduction. So last time, what did we talk about? We did the seminal work of two scientists. Gödel proved there are provable truths. And then following that, Turing, heavily inspired by the proof, almost the same proof in some sense, proved that there are unsolvable problems. Both of these guys used the technique of diagonalization to show such a thing, right? We followed Turing's proof and we were able to conclude that the halting problem is not decidable. And since there is no Turing machine for it, and again, halt is compares of machine words such that the machine halts on that word. Okay. And we were able to prove that there was no decider for halt. But then we said actually there's a recognizer for halt. We said halt was actually half decidable in some sense because there existed a machine that did not halt on all inputs, but it halted on the good ones. So in some sense, that's half a decider. But given that, we were also then able to argue that since halt is undecidable, but is recognizable, halt complement must not be recognizable. So at least we knew one language was not recognizable. The reason I point your attention to this argument is that we were able to argue about the undecidability of halt complement without a proof by diagonalization. There was no immediate self-reference. All we had to do was simply relate the solvability or unsolvability of a different problem to a problem we already knew to be unsolvable. And to formalize that notion of a relationship is simply a reduction. So we are going to prove many other problems are undecidable today, but without having to repeat tedious diagonalization proofs, we can perform a very simple reduction. So you may recall a reduction from 3510. This is prior to that, and in fact the reduction from 3510 was inspired by this one. So we write for A, B are languages. We say that A is mapping reducible or many-one reducible, so it's either mapping or many-one. Many-one is an older term, and it doesn't really make sense anymore because you're not really going from many to one. We say that there's a mapping reduction from A to B if there is a computable function f. And again, a computable function is in the sense that it is Turing computable. There is a Turing machine that halts at all inputs to compute the function such that x, we'll say, w is in A if and only if f of w is in B. And analogously, w is not in A if and only if f of w is not in B, right? The picture you should always have with these kinds of reductions are you go from good to good and bad to bad, but they need not be surjective or anything. So let this be B and this be B complement, let this be A and this be A complement. What happens is the mapping reduction maps all good things in A to good things in B, and all bad things in A to bad things in B. Right. This is the image we have of the reduction. And again, the Turing computable function f is one that must halt on all inputs, right? What difference is there between the definition given of a mapping reduction and the reduction you know from 3510? Maybe a minute since you've looked at NP completeness. But there's a lot of reductions you do in 3510. Do you notice a difference between these two definitions? Yes?
The other definition was super focused on mapping inputs and outputs, but this is more concerned about mapping good inputs to good outputs.
I claim the notion of polytime reduction in 3510 still requires good to good and bad to bad. The answer I'm looking for is that this only needs to be computable, but a polytime reduction needs to be an efficient translation in the sense that it's computable in polytime. So the reduction must be quick in algorithms. In computability, we don't care. We just we hope that the reduction exists. So in some sense, there is a Turing machine to compute F. We don't care about any notion of time. But it can relate solvability and unsolvability of problems. Why? The following four things are true. If there exists a reduction from A to B, then we may say the following is true. B is decidable, implies A is decidable. The contrapositive of that is also true, that A is undecidable, implies B is undecidable. Now that lets us prove problems undecidable without having to do a diagonalization argument, because we may simply reduce from here A an undecidable problem. So if A were to be halt and we were to successfully show such a reduction, then we've proven whatever B happens to be is undecidable as well, right? And by a similar argument, if B is recognizable, in some sense half decidable, then A is recognizable. And 4, if A is unrecognizable, and since there is not even a half decider for it, then it must be that B is unrecognizable. I will prove one of these to you. Let's prove number 1. Number 2 is just the contrapositive of number 1, and 3 and 4 will follow basically from a very similar argument. But if you can show 3 from an almost identical argument, that you can show 1. So let's just show 1. Suppose that we have a mapping reduction from A to B. And we're going to do less than or equal to and a little subscript M. The way to interpret such a thing is that A is easier than B, and then B is harder than A, or more unsolvable, and A is less solvable, right? So in the sense that if B is solvable, decidable, then A being quote unquote easier than B means that A should be solvable as well, right? So suppose we have a mapping reduction in such a form, then we know that there's this function f exists such that w is in A, if and only if f of w is in B. Further, suppose that since B is decidable, there is a decider, we'll call it alg for B. We give a decider alg for A. So let's suppose there's a decider for B, a machine that halts at all inputs, and let's suppose there is such a reduction. We give a decider for A as follows. Alg for A on input W, it's first going to do what? It's going to compute f of W, and then it's going to return whatever the decider of B says to do on f of W. That's it, right? Now, why does this work? You're trying to distinguish between good in A and bad not in A, right? You're given an input W and you're trying to say, are you here or here, right? So what you do is, you don't know, you compute the reduction over here, and then you can decide if a string is in B or not in B. So you know if it was in B, then it had to come from A, and you know if that it was not in B, it had to come from A complement. So you know by determining if it's here or here, you can infer if it was from here or here, right? Therefore, we see that this is a decider for A, and therefore that implies that A is decidable. This is such a Turing machine. Right? Questions on that argument? Here's how you prove 3. Replace the word decidable with recognizable. Suddenly it's a recognizer. Here's how you can prove the same thing for NP completeness. Let this be a polytime algorithm and let that be a reduction in polytime. Why is this a decider? Well, by definition, F must halt on all inputs. The machine to compute F halts on all inputs. So this step halts on all inputs. And since alg for A is a decider as well, we know that this line also halts on all inputs. So this halts on all inputs as well. So that's certainly why it's a decider, right? Not, let alone correct. Questions on that? Okay, we need to prove several problems now are undecidable. Actually, I think you previously had asked me, when is it useful or interesting to write algorithms that contain infinite loops? And the answer is, this is the only lecture that matters for. So usually it's bad practice. Here it lets you prove theorem. So that's kind of the moral of today. Let a second problem be this, we call it the acceptance problems for Turing machines. Consists of machine word pairs such that M not halt on W, but must accept W. Okay? It's called the acceptance problem for Turing machines. So given a Turing machine and a word, can you determine if the Turing machine accepts the word? Now, we know that the halting problem is undecidable. Given a Turing machine and a word, can you determine if the machine will halt on the word? I'm asking a different question. Does the Turing machine accept the word? Do we think it's decidable or undecidable? I'll tell you, it's undecidable. Why? We'll build that intuition. But basically, it just sounds kind of like a perturbance to the idea of halting, right? So in fact, a diagonalization proof exists to show that ATM is undecidable, and it's just a modified version of the proof of the halting problem. But we can prove it simpler than repeating the diagonalization by simply giving a reduction from halt to ATM. So we seek a computable function, f, such that f takes on input m and w, and outputs some, let's say, m prime, w prime, such that m comma w is in halt if and only if the output of the reduction is m prime w prime is an ATM. Now, I'm going to complete the reduction and then talk intimately about it for a second, because there is a lot going on. So, in the true spirit of the meta here, programs are both things that are executed and also things to be executed upon. So here we have 3 programs, maybe more. A program is taken as input by a program, which outputs another program. So what this means is, this is a program which outputs a program. So it's a piece of code that it's not a piece of code, it's a program to write the description of another piece of code. So there are machines writing machines, but it's not the case that anything is necessarily ever executed. I will describe to you what M prime looks like now. M prime, let's say on input, and let this be some generic input, let's say X, okay? It's going to contain M hard-coded. Let's do like that. Okay? M prime is written down by this reduction. It contains, as constants, just hard-coded into the description here, the description of M and the description of W. Now we're going to simulate M on W. Now, that line could get in an infinite loop, right? So, if it's the case that M, basically what we're doing is we're taking M prime and we're conditioning it on M. By saying M prime is going to simulate M on W, what we mean is that M prime is kind of going to do whatever M is supposed to do. So if M gets stuck in a loop, so will M prime, right? If M halts, so will M prime. If M loops, so will M prime. Then we just say accept X. Okay? So M prime is not going to do anything interesting except have an infinite loop in the case that M has an infinite loop, right? Specifically on a single input W. So then the reduction will simply take on this M, this W, and output this M prime and just some fixed string, let's say the empty string, right? Doesn't really matter. Why does this work? L of M prime is what? What is the language accepted by this machine? Yes?
Would it be the language accepted by M?
Not necessarily true, because they have different inputs. Let's say M prime rejects everything or something, then X is just any input to M prime.
How does X and W relate?
W is an input to M. However, from the perspective of M prime, it is just a random constant. This is the trick, and you'll see we'll have to redo this proof 3 times because every proof will kind of look a homomorphism of this one in some sense. So consider the two cases. Suppose M gets stuck in a loop on W. What do we know about the behavior of M prime?
It'll also get stuck in all of it.
Yeah, and if it gets stuck in a loop on all inputs, notice that no matter if the input changes for X, it does not change for this M and W. So it gets stuck in a loop on all inputs, M prime. If M gets stuck in a loop on one input, M prime gets stuck in a loop on all inputs. So in fact, this is either two things. It's either the empty set, or if what happens in the case that M does not get stuck in a loop on W?
It accepts W.
Yeah, let's say it accepts or rejects.
Or rejects.
Yes, so there's like a three value-ish kind of way to think about it. It's not just halt and not halt, but halt. If it halts, then it accepts or rejects, and then or loops, right? Something like this. So if this line completes, we don't care if it accepts or rejects. We just, okay, well, you accepted, go to the next line. We only hit this next line if this infinite loop is not an infinite loop, right? So if M halts on W, then we know we accept X for whatever X is. So we just accept all inputs. So in fact, this is going to be sigma star. So the language of M prime is one of those two things, but which thing it is depends upon M and W. We don't actually know what M prime's behavior is. So this is the thing. We can link behaviors of machines without knowing what the actual behaviors are. And that's the point of every reduction. It is a link. It is a connection. But we don't actually know what the connection is. But it does correctly go good to good and bad to bad, even though we don't know if it was good or bad. But it's still, if it was good, it's good, and if it was bad, it's bad. Questions on that before we actually do the if and only if? Right? Again, we need to show an if and only if part. So we're gonna do both ways.
I have a question.
Yes.
And how is W selected? Is that
The reduction. So this is not. Here's an important thing. M prime is never executed. M prime is printed by a machine which computes the function f. So it takes as input M and W, and it prints out this code of machine M prime by doing a little bit of string surgery and copying and pasting templates together to hard code whatever M is and whatever W is into M prime.
so? It's not an actual placeholder, but in terms of for our proof, it's not important what it is.
Exactly. You can think of this as mapping strings to strings, right? Good to good and bad to bad. You don't have to think of M and W and M prime as anything significant. Okay, so let's do the proof. Let M comma W be in halt. If M comma W is in halt as a string, we know that M on W halts. So we know that this line of code on M prime continues, right? So we know that M prime halts on all inputs, right? So then we know that M prime comma empty string is an element of ATM. Agree? Okay. Now suppose the input was bad. Suppose M comma W is not in halt. Then we know that M prime, we know that M on W loops. If this string is in this language, not in this language, then we know that M on input W loops. Notice how we're connecting an idea of a syntactic object to a semantic property, right? This being a string in a language is something about a machine doing something. That's kind of what every proof will rely on. If M on input W loops, so does M prime. M prime on the empty string will loop, right? And then if it loops, it doesn't accept it. So we know that M prime comma empty string is not an ATM. Either way, this is sufficient for us to prove that M comma W is in halt if and only if M prime empty string is in ATM. Done. We've proven then that we have performed a mapping reduction from halt to ATM. Now, we previously proved that if B is decidable, then A is decidable. So there's two things you could do. Just take the contrapositive and say that, well, since if A is undecidable, then B is undecidable. We reduced from halt to ATM, and make sure you go in the correct direction. Halt is undecidable, therefore ATM is undecidable. Another way to think about it is this. Assume to the contrary, ATM is decidable. Then use this reduction to decide halt, contradiction. One way you can imagine it is someone offers you a service. I claim I can determine the acceptance problems for Turing machines. You say, okay, fine. You craft a very specially sneaky input, and you trick them into determining if a machine halts. They claim they can determine if a machine accepts. You use them to determine if a machine halts by crafting this as your input. This will accept a string if and only if M halts on W. So if they can tell you if it accepts, you can use that answer to learn if it halts, if a different machine halts. That's kind of the moral. Yes?
So what does this give us? I mean, I know it shows us that B is decidable, if A is decidable or whatever, but so I guess, what is ATM?
ATM is really just kind of a syntax. This is our first reduction of today. ATM is really nothing more different than halt in some sense. The halting problem is undecidable. The acceptance problem is undecidable. That's all we've proven today. Yes. So it is undecidable to determine if a machine halts. It is also undecidable to determine if a machine accepts.
This ATM specifically?
Correct. Now, the other languages we'll do today are all, in fact, properties of Turing machines. Let ETM be the language of machines, not machine word pairs, but just simply machines, such that the language of this machine is empty. So for example, this language contains machines, not machine word pairs, just machines, such that the machines accept no strings. Now, that means they either reject all strings, that means they either get stuck into a loop on some strings but reject the others, that means they get stuck into a loop on all strings. Some combinations of these are the machines that are in ETM. We prove ETM is undecidable by reduction. But instead of we cannot do, it turns out, a reduction from halt to ETM, for complicated reasons we'll see later. This does not actually work. But what we can do is do a reduction from halt to ETM complement. Now, why is that okay? Why is proving the complement of ETM undecidable enough to prove that ETM is undecidable? Yes?
If ETM is undecidable, then we know, the complement of ETM is undecidable, then we know that ETM is undecidable, because if ETM was decidable, so would ETM complement.
Exactly. Another way to think is that the decidable languages are closed under complement. L is decidable if and only if L complement is decidable, right? Control F, return true, return false. So it's enough for us to prove the complement is undecidable, and as we'll see, that is going to work for us. Right. What's our reduction going to be? Actually, it's going to be identical. It's going to be, in some sense, the same reduction. We want a reduction that takes as input M comma W and outputs just a single machine M prime. Okay? This is the syntax of the two problems. Halt has machine word pairs. ETM has just machines. Right, so what's our M prime going to be like? M prime on input X. It's going to have M and W hard-coded into it by the reduction. And then we just simulate M on W, and if that line passes, then we just accept X. So, that's the reduction. You take on input M and W, the reduction writes down the code of this machine. Why does this work? Suppose that M comma W is in halt? What is the behavior of M prime? Well, to take a step before that, if the string M comma W is in halt, then we know that the machine M halts on the word W. So what do we know about M prime?
It also holds, or,
Yeah.
well, it accepts.
In fact, yeah, it's both. It halts because it's going to accept all strings. So in fact, since it accepts all strings, what is the language of M prime?
Sigma star?
Yes, it accepts every single string. But that is not the empty set. So that implies what about the code of M prime? If the language of M prime is sigma star, it is not the empty string. It is not the empty set. So it is therefore not an element of the set of all machines that accept no strings. Yes?
Why is the empty set not?
Sigma star? What if I did this, right? You know from set theory that this is true, right? That's all we're saying. It accepts not only one string, it accepts every string. Now that's not accepting no strings.
But why does, in this example, it does accept the empty set?
There's a difference between the empty string and the empty set.
But there you say L of M prime.
Okay. Let's finish the proof and then we'll come back to that, okay? Because in fact, it's conditioned, right? If we know this is true, then we know that sigma star is not the empty set. Now, suppose that M comma W was not in halt. Then that implies that M on input W loops, right? Which implies, what about the language of M prime?
Accepts no strings.
Correct. So what language, if it accepts no strings, what is the language?
The empty set.
Yes. Which implies that the description of M prime better be an element of ETM. Now to come back to your question, M prime has entered itself into a suicide pact with M, right? It is the case that the language of M prime will be either two things, the empty set or sigma star. But which one it wants to be is actually dependent upon whether or not M halts or not. So if it halts, we're just going to accept everything. And if it doesn't halt, if M loops, then so does M prime. And if M halts, we're going to accept every string and not be the empty set. So we don't actually know what M prime is going to do, but we know it's going to do something conditioned upon, in an if and only if manner, whatever M was going to do. This is enough for us to prove these two chains are such that M comma W is in halt if and only if M prime is not in ETM. So that's sufficient for us to say that there is a reduction from halt to ETM complement. Yes?
And ETM and ATM themselves are not, well, they're Turing machines, but they're Turing machines that also simulate another Turing machine.
ETM and ATM are problems in the sense that they are just sets of strings. And then those strings happen to be, the problem instances happen to be descriptions of other things. In the same way that we prove, for example, A to the n, B to the n is not regular, we're proving there is no Turing machine for a problem. In the same way that A to the n, B to the n is a problem. But the problem is now a little bit more meta because it's a problem about machines that a machine cannot solve. That's kind of what we're going through. So not only does there not exist a way to determine if a machine accepts a word, there also does not exist a way for you to determine, given a machine, if it accepts any string. Not just a fixed string, but any string. Is the machine empty? You cannot determine this. It's undecidable.
And so is halt also a set of strings then?
Correct, exactly. Now, it's interesting to note that it is a set of strings in the sense that it is pairs of machine words, in the sense that the pair is the string description of the machine. This is the code of the machine concatenated with the input to the machine. and we ask, does this machine halt on this word? That's that's the input to the halting problem. Right? We'll generalize this all today. Okay? Fine, determining properties about machines and machine word pairs, whatever. What about pairs of machines? I asked the question, is the equality of Turing machines decidable? Oops. Consists of codes of two machines, M1, M2, okay? That they accept all the same strings. Such a problem is also undecidable. By the way, here's an important reason this is undecidable. We are talking about the semantic equivalence of programs. Let's say you're an actual software engineer and you're working on something. You are doing a big rewrite of the code base from, I don't know, Java into some new language that is trendy, right? How do you know that your re-implementation of the program is identical? You can't ever mathematically prove it because such a problem is undecidable. So the best thing you can do is 10 million unit tests. There is no way to be with absolute certainty in general whether two different machines accept the same strings. They behave exactly the same. So determining equality of machines is an unsolvable problem. People in program analysis are very aware of this, and so they set their expectations reasonably. We'll talk more about program analysis today. But such a problem is also undecidable. Why?
What was the question?
Why is such a language undecidable? We want to prove a reduction, in fact, right? There's a few things we could put over here, but what's a good idea to put there?
Halt.
Yeah, we'll do that one later, but there's an even simpler answer we can put there. You can determine zeroness by determining equality. Do you agree that if you have equality, you have zeroness? So if you don't have zeroness, then you cannot do equality. We can reduce from ETM to EQTM, and since we proved that ETM is undecidable, so will EQTM. Here's the reduction. We're going to take a machine from ETM and output a pair of machines, say M1, M2. What should M1 and M2 be? We want M to be empty if and only if M1 equals M2 in the language sense. Maybe not in the string sense. I'll tell you. Let these two machines be called just M and M empty set. Or M empty set loops on all inputs, or rejects all inputs, we'll say. Let's just say rejects all inputs. Therefore, M is empty if and only if it equals, in the language sense, the machine that rejects all inputs. Because this is empty. Let's just do the proof. If M is an element of ETM, then we know that that implies that the language of M is empty. Well, that implies that the language of M is equal to the language of M empty set. Which implies that this pair of strings, M empty set, is in EQTM. Okay? Similarly, if M is not empty, if M is not in the set ETM, then the language accepted by M is not the empty set. Whatever it is, some string, it accepts some string. Then the language of M does not equal the language of M empty set. Thus, the string m comma m empty set cannot be in EQTM because they are not equal. Yes.
And so in the function, the m, the m is the m for ETM.
Correct.
Okay.
It takes as input something from here and maps it to something from here. You should always think about this picture. Good to good, bad to bad. This is enough. We've done the two if and only ifs. Two parts, P implies Q, right? So we know that M is an ETM. If and only if M empty set is in EQTM, where this is just the output of the reduction. Right? So if someone claims they can solve EQTM in general, they can actually solve it in this specific case. Therefore, they can't solve it. Right? Question?
In the image, does it matter which one is A and B on either side?
Yeah, let this be the one that's reducing from, and let this be the one that's reducing to. Okay. It's important that reduction go the right way, because if it goes the wrong way, reducing to an undecidable problem does not imply you're undecidable. In fact, you can always reduce to an undecidable problem, right? Every language can be reduced to an undecidable problem. Every decidable language, right? So now we need to answer two questions. First, we claimed that although halt was undecidable, it was the case that halt's complement was at least recognizable. But halt's complement, and we also used this argument to show that halt's complement was unrecognizable, right? So there must exist some obvious languages that are not recognizable. But in some sense, there is kind of an algorithm for halt's complement in the sense that there is half an algorithm for its complement, which is the original, right? So we said a language is recognizable if there is something that accepts the good inputs and rejects or loops the bad inputs. And we know that there can't both exist a recognizer for halt complement and halt. Both of those cannot be true. Halt complement still is, it's not recognizable, but it is solvable in the sense that its complement is recognizable, because the complement of the complement is just halt. So what that means is there is a recognizer for halt. So in some sense, halt's complement is kind of solvable in the sense that if something is bad, it rejects, and if something is good, it loops or accepts. Kind of complicated there. So we ask a more general question. Let L star TM be the co-recognizable languages. In the sense that L is an element of the co-recognizable languages, if and only if L complement is recognizable. Quick, give me an example of a co-recognizable language.
ETM, EQTM?
Those arguments are going to be complicated, but that is true, I think. But actually not EQTM at least, but halt is actually co-recognizable. No, halt complement is in fact co-recognizable because halt complement is in fact recognizable.
Okay, gotcha. Oh.
Yeah. So in some sense, it's still in a class that can be defined by an even looser definition of algorithm. Let me give you the world map. Okay? This is the solvability of all knowledge. The universe looks like this. Okay? First off, at the first rung of hell are finite languages, right? We have the empty set, we have sigma to 7, whatever these happen to be. You know, AAB. Those exist there, right? Next, we enter the regular languages, which are infinite but patterned. So this is LDFA, LNFA, what else did we do? Regular grammar, regular expression. There's so many things that accidentally happen to be equivalent to the regular languages. They're highly patterned and memoryless. These contain things like A star, what else? A star, B star, and so on, right? A union B, things like this. We pumped out of those to get the context-free languages, right? These were LCFG, LPDA, and several things were in here. First off, we had, of course, A to the N, B to the N. We also had WWR. We had the Dick language. There were some other things that were probably in there, right? And then we pumped out of those, and we talked about, we didn't actually prove anything was context sensitive, so let's just ignore it from the map for a second. But then we proved that some of the languages were decidable. So I'm going to draw it like this. Okay. Some languages were decidable in the sense that there exist algorithms for them, right? So this includes like A to the N, B to the N, C to the N, but also obvious things like primes. What else goes here? Basically anything that has an algorithm, right? But we know that some things are not decidable. So let us draw the map to look like this. And let this be L star TM. These are the recognizable languages, right? So what goes here is halt. And we know by the Church-Turing thesis that this is kind of like a demarcation about things that we can solve. Anything lower on the level than this border here is solvable and simpler in some sense, right? The more left you go, the simpler you are. And there's anything with an algorithm has to go here. Anything. As long as the algorithm halts on all inputs. We know that there are many problems that are recognizable but undecidable. Halt is such a problem. Then up here we can define the co-recognizable languages to be those which are not decidable but whose complements are recognizable. So what that means is that halt complement is at least co-recognizable because halt is recognizable, right? Now, why have I drawn the intersection of, what is the intersection of the recognizable and co-recognizable? Suppose a language is both recognizable and co-recognizable. A language is recognizable and its complement is recognizable. What does that tell you about the language?
Would it make it decidable?
Correct. So in fact, the intersection of this and this is exactly this. So the picture, that's why the picture corresponds that way. Everything that is decidable is not simply a subset, but is exactly equal to, right? ATM, let's just plot some of the others. Is ATM recognizable? By a recognizer, again, we mean a semi-decider in the sense that we say W is in L, and if and only if M accepts and halts, and we say W is not in L, if and only if M loops or rejects, right? And that's what we mean when we say a language is recognizable. So there's at least a half decider, a semi-decider for it. ATM, semi-decidable, what do we think? Why?
It's a variation of the halts.
Give me the recognizer though, describe the code.
If halt stops on it, then...
Not without the reduction necessarily, but just suppose I asked you to recognize the language. Given a machine and a word, determine if the machine accepts the word. But do not determine if the machine does not accept the word.
If it stops, if it halts.
Yeah, so I guess the answer I'm looking for is just simulate M on W, okay. And if it accepts, not just if it halts. If it rejects, also reject, but if it accepts, you accept. That is a recognizer So we know that ATM is in fact recognizable. And by definition, then ATM complement is recognizable, okay? What other languages did we do today? ETM. Is ETM recognizable or is complement recognizable? Can you determine if a machine is empty? Can you determine if a machine is not empty?
I would say that ETM is recognizable.
Give me a machine that determines if another machine is empty.
The second machine is run on the first machine with the input.
Ah, but there's no input.
With any input or with a constant?
This is actually a very complex thing, but I'll tell you that it is the case that ETM complement is in fact recognizable, but ETM is co-recognizable. Why is that the case? I claim that, so for example, if ATM is, you can determine if a machine accepts a word by just running the machine on the word and waiting for it to accept. That's a way to recognize, right? You can determine if a machine is not empty by trying to run it on all inputs, then waiting for it to accept. Now if it accepts a string, you are convinced that it is not empty. So you can determine if a machine accepts a word by just seeing it accept. Then you know it's not empty. But you'll never know if it is empty because you don't know if that's never going to finish. Now there's a small technical question. How do you, oh, my camera was not moving. How do you determine if how do you run a machine on infinitely many strings?
You can. Or do you run them in parallel?
Yes. Now how do you run, now when you run two strings on a machine in parallel, that's possible. How do you do infinitely many strings? This requires creativity. It's possible.
Would you run it on a set? The infinite set?
Yes, but it's complicated because I'll just tell you the answer. You have a list of VMs. And then you say for W in sigma star lexigraphically, add MW to VMs, increase we'll say for VM in VM, simulate one step. So what you're going to do is first add the machine on the empty string to the set of VMs and simulate it for another step. Then you're going to add a second VM to your list, the machine on the string 0. Then you simulate both of those machines for one step. So in some sense you have M, empty string, let's say M0, M1, M00, right? You simulate this for one step. Then you simulate every time you simulate something for one step, you add a new VM to the list. So you add this to the list and then simulate both for one step. Then you add this to the list and simulate all of them for one step. Then add this to the list and simulate all for one step. Right? So what that means, if the machine accepts any string, you'll eventually find out. It'll take you an increasingly and tedious amount of time, but it will eventually work. Part of the fun in computability is you get to write algorithms for things that nobody cares. I mean, like this is not practical in any sense or efficient. There's no reason for you to ever do this, but it proves something, that if a machine accepts a word, any word, you can find out eventually. So you can always determine if a machine is not empty. You can never determine if it is empty, but you can determine if it's not empty by just doing this kind of search. So the complement is recognizable, and therefore ETM complement, which is itself is co-recognizable.
That's valid because each step is finite.
Exactly. You simulate each for a finite number of steps. Eventually, for example, how many steps does it take to get M on the empty string, to like the 100th step? You're gonna have 100 VMs in your list, and each time it's gonna increase, but you will eventually. It is kind of like a way the diagonalization for the rationals occurs, if you think about it that way, right? Complicated technique, it's called dovetailing, but in a funnier way. We get back to the question at hand. This is the map of the world. Yet, I claim problems were undecidable, yet it appears that everything fits nicely into some category. Why is... Is there anything out here? Is there, ETM is at least solvable in the sense that its complement is recognizable. Is there anything that's not recognizable or co-recognizable? Is there something stratospheric that it doesn't even have an algorithm, half an algorithm, for it or its complement? Does such a problem exist?
It would be unfeasible.
Well, yeah, exactly, that's what we're trying to prove. But everything we've done so far on this chart is feasible in the sense there either is an algorithm for it, or there's an algorithm for its complement, or half an algorithm, a recognizer, for either it or its complement. Everything fits in a bubble. That's not good. I claim there are problems that are totally unsolvable, more unsolvable in the sense that they cannot be, they are both not recognizable and not co-recognizable. What would such a problem be? What is a problem you can imagine you cannot determine it or its complement in a halfway?
Are you asking for like a machine?
Any kind of problem, in the sense maybe a set of strings of machines.
So it would have to, the complement and itself would have to be unrecognizable.
Exactly, exactly.
Which means you can't even decide
Exactly.
half of them.
Exactly. So in some sense, it's even, quote unquote, harder than the halting problem. Such problems I claim exist. Two arguments. First, counting argument. Everything here can be described by strings. They have machines for them. So a little bit of bijection math, and you can say that this whole thing is just a countable subset of the entire universe. This whole thing is microscopic in the context of the power set of sigma star. Right? There are uncountably many more problems to solve. No matter how you phrase it, this whole thing, this whole chart is just that little dot, okay? The universe is vast, we can't see any of it. But I claim that there are problems we know that are way out here, and I'll just tell you, it's gonna be EQTM is not even recognizable or its complement. You cannot even determine if two machines are gonna be equal or not gonna be equal.
And is that what that says?
Almost. We have to finish the math to show it. Let's formalize, let's leave this proof here and try to formalize how we can prove that ETM is both it and its complement are unrecognizable. So, first some properties about reductions. And I claim most of the following without proof. One, A reduces to B if and only if A complement reduces to B complement. Why is that true?
Because otherwise they would be undecidable.
Not necessarily, forget the decidability. This is a question about reductions. Why, if there's a reduction from A to B, is there a reduction from A complement to B complement?
If you can find what's good, it maps both ways. If you can find what's good in A, you can also find what's bad in A through the reduction.
Yeah. The reduction is supposed to take good to good and bad to bad. Therefore, it can also take bad to bad and good to good.
Okay.
Yeah. If A is mapping reducible to B, and B is mapping reducible to C, that implies that A is mapping reducible to C. Why is such a relation transitive?
If you can map A to B, you can map B to C, then you could use B as the map from A to C.
Yeah. Given a reduction A to B with F and a reduction B to C with G, just compose them, and a composition of computable functions is computable. G of F, this will go by G of F. Right? Okay, composition, okay, fine. If we have a reduction A to B and A is unrecognizable, that implies that B is unrecognizable. We actually just mentioned that at the beginning. That was the fourth point of those four, right? So we already know an example of an unrecognizable language. It's halt complement. So in fact, all we need to do is prove that halt is unrecognizable, we simply need to prove that there is a reduction from halt complement to EQTM. That would prove that EQTM is unrecognizable. Doesn't show it's unco-recognizable, but just shows it's unrecognizable. It's somewhere here. Then we'll show it's not here, so it must be here, right? But that's equivalent to showing that there is a reduction from halt to EQTM complement. Right? I claim there is a reduction from halt to EQTM complement. We can just throw a little bit of math at it without having to do the reductions. We gave a reduction first off from halt to not ETM but ETM complement, right? And then we gave a reduction from ETM to EQTM, right? But that implies that there is a reduction from ETM complement to EQTM complement. So take this one. By transitivity, there is a reduction then, halt to EQTM. Therefore, and this is true, then so is this. EQTM is unrecognizable. Yeah, without having to do a reduction, and in fact you can do the reduction, it's actually not hard. I think the math is fun, more fun though. Okay. We've proven that EQTM is unrecognizable. Now we want to prove that EQTM complement is also unrecognizable. So we reduce from an unrecognizable problem, halt complement. Well, that's the same as just giving a reduction straight from halt to EQTM. So we just need to give such a reduction, and that'll prove that EQTM complement is unrecognizable. Yes?
So on the left side of that math, so halt complement reduce, or is it reduces to? I forget.
Correct.
Reduces to EQTM. That we hadn't proved yet.
No, we had not proved this. Want to show this. Correct.
And then we use the fact that we know halt reduces to ETM complement.
Yes, we proved these two statements together.
Okay.
Yes. Those we've done previously today, and then together, this one by that rule implies this one. Then you chain this one and this one to get this one, which is this one. So, yes. Okay.
Thank you.
So let's just give the reduction from halt straight to EQTM. And let's just remind ourselves of the syntax. We want to go straight from halt straight to EQTM. Combined with our previous work, this will prove that EQTM is both unrecognizable and unco-recognizable. So we want a reduction that'll take M and W from halt and output a pair of machines M1, M2. Such that M accepts W if and only if those are equal. Okay. Let M be M prime and let M2 be M sigma star. Such that M sigma star accepts all strings. And we construct M prime on input X as follows. It's going to have M hard-coded, W hard-coded, into it by the reduction function. It simulates M on W. And if that accepts, it's just going to accept X. Isn't it interesting that we've done the same reduction 3 times? Like it's the reduction just works for all of them. We'll talk about that later, but let's just prove that it works. If M comma W is in halt, that's true if and only if M on W, not true, let's not do if and only if, that's true, that implies that M on W halts, which implies that M prime accepts all strings because it passes this line of code to this one, right? But then that implies that these two are equal. Which implies that the pair of those strings better be in EQTM. Right? Similarly, if M on W is not an element of halt, that implies that M on W loops, which implies that M also accepts no strings. So L of M is the empty set. And is therefore not equivalent, the set of strings it accepts is in fact not equivalent to this M sigma star machine. All in all, we see that M comma W is an element of halt if and only if this pair of machines, M prime comma M sigma star, is an element of EQTM. If someone claims they can solve EQTM for you, great. Use them, carefully crafted input that tricks them into solving the halting problem. But you know the halting problem is unsolvable. That's what the proof shows. We have therefore sufficiently proven there's a reduction from halt to EQTM. It's the same reduction, in fact, right? So where are we? This is the universe. This is every problem we have ever talked about, everything we've ever known. We did so many languages. We spent like 3 days here, 4 days here, 3 days here, and now we're spending some time way out here, right? And how much of this is relevant, really? In the sense of the church-Turing thesis, the only thing we really can talk about is things here, right? Things here only in half a sense, but there's nothing out here. Yet, we kind of can argue through self-referential arguments and reductions, which are really just kind of relationships, that there are things out here that we know we can't know about, but we know that they're there. And that's kind of interesting, I think, in the sense that the light is off, but you can kind of feel around in the dark, and you know that it's really deep and empty out there. But you don't know, you know that there are things out there, but you don't know anything else. Kind of a strange argument. But this is the map of the known universe of every problem that is solvable. It can be placed somewhere on here. Or, as we know, in fact, not on here, way over here somewhere. Questions on that? Yes?
So, for this proof, those last 2 lines where you're saying if MW halts or is in halt and if MW is not in halt, that's kind of like, well, obviously that's most of the proof, but how, what I'm confused about is specifically how L of M prime contains, how you can differentiate between the sigma star and the empty set.
We actually don't know what L of M prime is. But like with the other proofs, it's either the empty set or it's sigma star. But in fact, both of those are regular languages, if you think about it. But what's important is which one it is conditioned upon the behavior of M and W. It enters the suicide pact. If M is going to do something, so is M prime. If M is not going to do something, so is M prime. But it doesn't know what M is going to do beforehand. It's also important to note that the reduction simply writes down the code of M prime. It doesn't actually run it. Nobody actually runs M prime because M prime would then run M on W. But in no way is the code of M prime actually executed. In fact, what's happening is that the reduction simply writes down this piece of code with the property, such that this if and only if it proceeds.
So it's not actually for solution, it's just to demonstrate.
Exactly, the connection. You can connect the problems even though you can't solve either.
Okay.
Suicide pact. Okay. Final questions? Let's take a break.